Okay, so here it is, the dreaded roller coaster problem. Take a look. I think a lot of people are confused about this being a roller coaster, and it is. It's basically, here's what happens. These two blocks collide, and they go up through this, and then up the ramp, and they actually stop here to turn back around. Not both blocks, just this one hits, and only one of them goes up, and that's right here. So, and drawing is not to scale. So, objects 1 and 2, pictured above, have equal masses. Good to know. Both of them are m. They are situated on a frictionless track. Also good to know. That's like a really important thing. Where object 1 has an initial velocity of v naught. Object 1 and 2 experience a perfectly... Okay, so this is a big implication here, which is annoying. Since object 1, which has a mass, I'm going to call it m1, has a velocity of v naught, the implication here, not so much from the picture, is that the velocity of 2 is 0. It doesn't explicitly say that it's at rest, but it's very much implied, and that would be mass 2. Sometimes if you just can't figure out what it's talking about, just go with what you think. If you're concerned about it, write down that that was the assumption you were operating under. Okay, so it says objects 1 and 2 experience a perfectly elastic collision, which results in object 2 having a velocity of v naught. Okay, that makes sense. They've got the same masses, so they're going to hit. Then object 2 is going to have a velocity of v naught, and that more than likely means that 1 would stop. So we're pretty much done with 1. Okay, so object 2 proceeds down the track, which of course is frictionless, and travels around a perfectly circular loop. Okay, this is the perfectly circular loop. I'm going to switch colors here. This is the perfectly circular loop right here. It says that it has a radius of RL. Because why not subscript everything? RL is much greater in size than the objects. That would mean they're not drawn to scale because they're not that much different. At the top of this loop, object 2 has a speed of v up. Object 2 then completes the loop and proceeds up the ramp to a height of h, where it momentarily rests and travels back down the loop. Okay, so that's kind of like what I figured. Got a lot of extra information on this one. So it's right here at v up. And I don't know if this is going to be important or not, but v up, since this was frictionless track, no force of friction. This is a frictionless track. V up is going to equal the same speed as that it entered the track with, which was v naught. So v up and v naught are the same thing. Okay, and it's going to continue to have that speed all the way to here. Like this is frictionless, to where it starts to lose some of its speed because it's going up the ramp until it stops to change direction. I'm going to put v just in general equals 0. And we're only dealing with one object here. So I've kind of like drawn all over that. So let's see what the first question actually says. Okay, it says derive an appropriate equation for height h in terms of mass, RL, V up, and G. I just wanted to show you that. I'm using a highlighter. Unfortunately, I won't get one on the test, but I'm using one here because it's kind of getting messy. Okay, it said mass, which would be, it could be either one of these. V up, which is right here. R, which is part of the loop thing, and height. So, right there, it looks like I am just dealing with the second half of this. Drawing a comic strip or like, drawing over the drawing, just getting an idea of what would happen playing with stuff on your table, whatever. So anyway, this wants us to derive a term of M, R, L, V up, and G for H. Sometimes it helps if you just put your letters here. I'm noticing something about my letters. I've got M, G, H. That's probably good to know. Um, but when they ask you to derive an equation, here's how it goes. If you have a free body diagram, it's more than likely Newton's second law. If you don't have a free body diagram and you have two objects, it's probably going to be momentum. In this case, it was tricky because it looked like you had two objects, but if you really read the question, you would see you're just looking at one. You're just looking at it basically from here, not even from this part over here. You're just looking at it from when it's at the top. So since we have one object and it's an isolated system, this is going to be conservation of mechanical energy problem. So I would put isolated. Okay, so I've got isolated system, no outside forces act on the system. I should have put this up here earlier, but remember, this is probably on Earth or some other planet. Assume it's Earth unless told otherwise, but be careful, make sure you check. All right, so no outside forces act on the system, therefore mechanical energy is conserved. So I need to look at my mechanical energy up here at the top. It has got, we know it's moving, so it's going to have kinetic energy. And we know that it is above the ground, like right here. So we know it's going to have potential energy due to gravity. Let's see that use of G. All right, and we just need to know how tall it is. And it so happens it's a circle, so this would be radius L, and this would be radius L. So that's radius L plus radius L to radius L. It's fine to do your work up here. Actually, I like to do that, but you just need to make sure you put it down here as well, where you're supposed to answer. So mechanical energy equals mechanical energy prime. So it starts at the top with kinetic energy plus potential energy due to gravity. And let's see what it ends up with. Okay, it comes up to the top where it is stopped, so there is no kinetic energy. K prime equals 0. I'm just doing that to remember it. I don't have to write that in the equation because it's 0. But you do have this height, so you do have u sub g prime afterwards. There is a value for that. So that's going to be the end of the equation. U, for this part, g prime. Now I'd break this up. Kinetic energy is m, and I'm going to use the capital M they want me to. V, and it's going to be V up squared. So mass speed squared over 2 plus potential energy due to gravity is weight. So big M, little g, and then height. And the height for this is 2 r sub L because it's twice the radius. It's the diameter of the loop thing it's in. And it's going to equal your height, your potential energy due to gravity because of the height it ends up at. So big M, gravitational field, capital H. Okay, so you're pretty much there. You just need to solve it for H. Let me show you how I do that. Okay, and then the ultimate laziness thing here, which you are more than welcome to do on the test. I have just solved for, I just moved mg from this side. I just put this in parentheses and put 1 over mg. In all honesty, you could put just a line under it and do the whole thing that way. Don't try and simplify or like distribute this, please. Just leave it messy. Just show that you know that this mg right here goes to the other side. And then I just put h on this side and scratch that out because I was being lazy. So let's look at the point breakdown on this. This is a three points of this, and this is a, let's see, this one's a 7-point question. So isolated system, no outside forces. You don't have to put that on every single one of them, but do just in case. Basically identifying that it's conservation of mechanical energy and putting that it's kinetic and potential to potential gets you a point. Okay, plugging these equations in, like mgh and 1/2 mv squared, plugging them actually into this is another point. And for having the right answer is another point. Okay, on to the next part. Okay, so part B wants to know, they want to change this up. The speed of V naught is doubled and the process in outline part A is repeated. Object 2 reach a height that is equal to, less than, or greater than 2h. Well, I would go back to the initial energy conservation thing, you don't have to restate isolated system and stuff. To me, the way I looked at this is you had potential energy due to gravity plus kinetic energy equals UG prime. So basically, we're looking at how speed, so it would be 2v naught right here. Speed is doubled. That's going to affect your kinetic energy. And then the outcome would be 2h. So the part, they want to know if that's true, if you have 2v naught. So the part that this would affect would be the potential energy due to gravity prime, because that's where the h is, and this is where the v naught is. So I would put this, I would state this expression, and K is directly proportional to V naught squared. Because we used V up before, but remember that was equal to V naught, like we did that in the drawing. V naught squared. And K is directly proportional to UG prime. UG prime is directly proportional to capital H. Therefore, I'm kind of going into this other place. H is directly proportional to V naught prime. And I might put over here V naught equals V up. That's probably overkill, but just so you know, because we did that with the collision. So if this is true, if I have twice the speed, I have like 4 times the height because it's squared. So I'm going to check. Put an x next to greater than. So this is perfect. That's fine. And if you're not writing with a weird pen on a computer screen, you probably have plenty of space. Okay, scoring on this one, this is worth 2 points. Basically, you had to have both things. You had to have, if you didn't have both, you didn't get any points. So you'd have 1 point for checking the right thing, and another point for something about kinetic energy going up with potential energy in this relationship. Stated somehow. You can write it in a sentence, you can have equations, you can have anything like that. But y'all are all pretty good at proportionalities and they're fast. That's my suggestion. So 2 points for that one. Okay, this last one's kind of weird, and frankly, it's an algebra trap. It's just a time sink. When you see one like this, if you have like something to derive, deriving things is usually 3 points. And then if you have one checkbox, I mean, worst case scenario, you had the first part of this, which is 3 points. Like question 1, anytime derived, just assume, let's just say assume derived questions are 3 points. Then you have a checkbox. Worst case scenario, this was 1 point. It wasn't. It was 2 points. But say it were, this would still only be max 3 points. And you're about to see how like it can get, if you just don't see it algebra wise, sometimes it pops out at you, but if you just don't see it like instantly, it's a huge waste of time. Be careful of these ones they tack on at the end of problems that you're like, what? Why would you add an extra block? Watch out for those. So anyway, let's look at this. We have the objects 1 and 2, which each have a mass of m, same thing we had before, are now placed on a new frictionless track. So that's important. That means mass is not super important in some situations, as pictured above. Assume that v1 is the lowest speed that allows object 2 to clear the dip. So they're doing the bounce, or they're ricocheting off of each other thing. That allows object 2 to clear the dip on the track. And that would be true for an object of any mass because it's a frictionless track. It's magic Disney stuff. Object 2 is now replaced with object 3, which has a mass of 2m. This is depicted below. So we've got, let's see, we've got m for this one. That's supposed to be an m, and then this one's 2m. Okay, objects, let's say objects 2 and 3 undergo a perfectly inelastic, so that means that they're going to fuse. Okay, perfectly inelastic collision in which the objects fuse. What do you know? And travel down the track, which is frictionless. Determine the lowest initial speed for the objects to clear the dip in terms of v1. Well, here's what we know about v1. since this is a frictionless track, any object that you have on it would need a velocity of v1 to clear the track. And these two things stuck together, which would be like something like this, are going to be no different. We also know that now, since they're stuck together, their mass is going to be 2m plus 1m, which would be 3m. Okay, so since we are dealing with two objects, there's no outside forces or whatever, we're dealing with a conservation of momentum. Little p arrow equals a little p arrow prime. And your 2 starts off at rest. So your beginning momentum is going to be 2m. I'm going to say like a v3. And it's going to equal, since they fuse, a mass of 3m, because we added those two masses. So when they stick together, it's 3m. So we're going to have 3m, because remember, most valuable player, because we watched the football video on this. That's your momentum equation. Anyway, 3m, and then its velocity, because they want the minimum. The minimum is v1. So it's going to have to be v1. So they want it solved in terms of v1, and they want to know the lowest initial speed. So that would be v3 right here. So we just need to solve for v3. I'm going to divide by 2m. Goes away. You divide this by 2m. And remember, these masses are the same. The m goes away. So therefore, v3, or whatever you want to call it, they didn't define it, is 3v1 over 2. And the points on this one are kind of messed up. Basically, yeah, you had to have the whole thing. Okay, so you get a point for having this, the correct conservation of momentum. Like, not just this, it's got to be plugged in. And you get another point for the correct answer. So that's 2 points. I would have probably just done this part or put something about conservation momentum and saved this one for last.